Hi, my name is Alex Tong, and today I'll be talking about our paper, Interpretable Neuron Structuring with Graph Spectral Regularization. So we know that there are many interesting methods developed in the past few years that help to interpret and diagnose convolutional neural networks. All of these methods for understanding convolutional neural networks apply to images and to some extent sequence data sets. But none of these methods work on unstructured data. In this work, we are mainly concerned with data that does not have this convolutional structure, so we cannot apply methods that rely on this. So the question we explore in this work is how to make the layers of a fully connected neural network more interpretable. What do we mean by interpretable? All of the networks are already interpretable as we know exactly how each feature is calculated and exactly what changes would change the output. However, this is not what we mean by interpretability. We would like to make the patterns and the features more apparent to the human eye. A fully connected layer is randomly ordered, and this presents challenges in high-level understanding. In a real brain, there are a lot of neurons, too many for our current measurement tools to keep track of. However, brains are extremely structured, and many of our tools to understand the brain exploit this structure. fMRI data is often segmented into activations of functional regions for a high-level understanding. Getting a high-level understanding in this way is both easier and more difficult for artificial neural networks. Real brains have some stability between individuals, in that most people have the same functional regions in roughly the same locations. Artificial neural networks, on the other hand, are generally randomly initialized and are not normally designed to have such localized regions. Our goal here is to encourage the network to have similar localization behavior as a real brain. We will first present an example where we encourage a layer to have smooth activations over a predefined graph. We will use a regular lattice structure graph for ease of visualization, but stress that our method works on arbitrary graph structures. We will then extend this to a second example where we do not want to enforce a predefined graph, but would like to learn the graph that best fits the data. So going over this example, we take a dense MNIST classifier and focus on one of the fully connected middle layers with 64. We lay this out in a grid graph pattern and add a smoothing penalty, as well as adding a convolutional classifier. The grid graph pattern allows us to do standard convolutions on top of it. However, for an arbitrary graph, we could also do graph convolutions, which are an interesting topic of future work. In a standard dense classifier, the activations on this layer are random, but somewhat similar for each digit within the class, or grid classifier at least. The goal here is to structure the activation space of this layer using these two additional structures. Notice here, the beginning of the network is fully connected. Thus, this network architecture can work on unstructured data types, not just using the highly structured space of images that we use here for a conceptual understanding. To do the graph smoothing, we use the Laplacian, a standard term used in graph signal processing, which is the degree matrix minus the adjacency matrix. This allows us to penalize the sum of differences along the edges of the graph in an efficient manner. For each MNIST digit, we average the activations over the entire class of the test set. For a standard network with no graph smoothing and no convolution, the activations are distinct for each class, but not very intelligible to the human eye. With a convolutional decoder and no smoothing, we do not see much effect. Adding smoothing, we can see how the activation space is smooth so that each node in a layer is similar to its neighbors. However, combining smoothing and convolution, we get a distinct activation region for each digit. Now, we have a set of neurons that are associated with each class. Going back to the brain analogy, we have constructed a network to have functional regions associated with each class. Here, we further examine the functional regions that result from a combination of convolution and smoothing. We segment the 64 nodes into distinct regions by the argmax across classes. You can see this on the right. Each neuron has a digit that it responds most to. We also show some examples of correctly classified test digits and incorrectly classified test digits. Here we can see that the incorrectly classified images, like the 9 that is classified as the 7, both visually looks like a 7, but also has activation primarily in the 7 space of our layer. For the 3 that is misclassified as a 7, it has some activation in the 3 space, but also has some activation in the 7 space. For the correctly classified digits, their activation is related to how we might make mistakes. The second 9 that is correctly classified looks possibly like a 0 and has some activation in the 0 space. This type of map allows us to examine at a high level some aspects of the data, even if the data is not amenable to convolutions. Moving on, we extend this to the setting where we'd like to learn the graph along with the network. This might be the case where you know your features have some structure, but the structure is unknown. Genes are known to have a regulatory structure characterized by some graph. However, these structures are only partially known. Here, learning the graph would correspond to learning a graph between the high-level features, or gene modules, that may be related to each other in the dataset, but not have a structure that can be identified using standard linear methods like covariance. To learn a graph structure, we use the same tricks as before, but make the graph based on the activations. This requires an EM-like iterative algorithm where we generate a graph using a kernel from the features, smooth the activations along that graph, and repeat the process. This procedure, along with a few tricks, see the paper for more details, gives us a way to evolve the graph structure to fit the training data. Here, we have a biological data set of developing T cells in the thymus that has a mostly linear structure that branches into two portions at the end. See top right, fate plot. We can see that over training time, the graph of activations evolves from a randomness to a near linear graph. We can look at the activations at different portions of the graph and see that, like MTIST example, there are localized regions for some states. These represent connected gene modules along the trajectory. So just in summary, fully connected layers have no natural structure, so we can't apply convolutional interpretability methods. However, by imposing a graph structure, we can create a high-level locality and activations much like a real brain. Finally, we can learn the graph structure from the data in an iterative process if we don't know the graph structure a priori. Thanks for listening. I'd like to thank all my co-authors and the rest of our lab for their help, as well as the Neuron lab and their feedback on the work. Please check out the full paper if you're curious for more details. You can find our lab website with a code for the project at the links at the bottom of the slide. Thank you.